Okay, so currently quantum optics is undergoing a renaissance, and squeeze states, our main interest goal today, so-called non-classical states, are promising resources when we talk about quantum technologies. Moreover, some precise machines are being made in order to better observe some really violent events in cosmos, things like black holes colliding, galaxies merging. So today we will talk about the challenge in the measurement, and it is called quantum metrology part. So dear Open Readings Conference participants, dear researchers, dear colleagues, guten Tag, willkommen zu diesem Vortrag, welcome everyone. It's Thursday, it's the third day of Open Readings Conference. And I am Mažena Mackoit-Sinkevičienė, theoretical physicist from the Institute of Theoretical Physics and Astronomy from Leibniz University and Center for Physical Sciences and Technology. And today, it's a huge pleasure for me to introduce our keynote speaker, Professor Michèle Heurs. Professor Heurs completed her PhD at the Institute for Gravitational Physics in Hannover in 2004. From 2005 until 2007, she worked as a research fellow at the Max Planck Institute for Gravitational Physics, so-called Albert Einstein Institute in Hannover. And in 2007, she commenced a research fellowship at the University of New South Wales in Canberra, Australia, within the quantum electronics group of Professor Elanor Huntington. So everything is connected to quantum. She returned to Germany to build her own group, yes, quantum control group, within the Center of Excellence for Quantum Engineering and Space-Time Research at Leibniz University in Hannover, Germany in 2010. And since 2016, she holds a permanent professorship at Leibniz University. The position carries the denomination, we already know, so non-classical laser interferometry. Applications are aimed for those future interferometric gravitational wave detectors, precision metrology, and quantum optics. Moreover, I would like to say that Michèle is a long-term member of the LIGO Scientific Collaboration and has been a council member of it since 2015. So it's really impressive. Research interests include non-classical laser interferometry, coherent quantum noise cancellation, measurement-induced entanglement, motor controls, quantum information, all quantum science. Yes, so I'm really looking forward to this lecture with non-classical states of light. Professor Heurs, the floor is yours.
Thank you, Mažena. And thank you for having me and inviting me here. It's been a pleasure. Unfortunately, I could only arrive last night, so I'm a little bit tired, but you will not notice because I'm very excited to speak here today. At least I hope you won't notice. So I'm not sure if you can see this very well because it's nice and bright in this beautiful auditorium. This over here is actually an image of, well, it's not a real image, it's just an artist's impression of the merger of two neutron stars. So, why am I showing you this? I'm actually, you know the expression a wolf in a sheep's pelt, right? I'm a sheep in a wolf's pelt. I'm a quantum optician working in the field of gravitational wave detection. And that's cool because when I was a young student, I wanted to be an astrophysicist, but I went into quantum optics. And I then became an honorary astronomer or astrophysicist by virtue of us then finally detecting gravitational waves. But this is about the science, and I'm very excited to tell you a little bit more about quantum metrology. Now, you might not exactly know what quantum metrology is, but metrology is the science of measurement. And if you want to do very precise measurements, we're all very macroscopic beings, so if we walk around and we say, what is this? About a meter. I'm kidding, it's a joke, right? This is approximately a meter, right? So from the bottom. So that's a very bad measurement. But if we want to do very exact measurements, we have to have very precise measurement devices, and that's what this talk is about. And one very good measurement device to measure with is light, by means of, for instance, interferometry. However, if you make measurements at very tiny scales, at some point quantum effects will become limiting. And we all, I'm assuming, you all know here in the room, and please do shake your head if I ask something and you don't know. There's no shame in that, on the contrary. You all know that there is quantum mechanics and there is the Heisenberg uncertainty principle, right? Perfect. That's good. You're all awake. Everyone's gone through the low after lunch. That's good. You've also had coffee, I suppose. And so when you come to the point where quantum becomes limiting, then you have to do quantum metrology. Okay? So simple explanation of a complicated sounding word, I hope. Now, as I said, I'm an honorary astrophysicist now, so I'll show you a visualization of the merger of two black holes. This is not real, it's not even a simulation, it's just an animation. And maybe, hopefully, you can see over here these black dots. Those are the Schwarzschild radii of the black holes, the two in their dance of death, and then they're going to merge like, well, they should be merging any second now. Now. Well, wait, no. Now. Okay? So two black holes become one, and when black holes merge, black holes are very simple creatures. They only have very few characteristics. They have mass, they might have spin, and they might have charge. Let's assume mass is the important bit right now. If you have one black hole and another black hole and they merge, after that merger, the information from the individual black holes that they were made out of has to be gone. Because now the new black hole only has a new mass, a new potential spin, and a new potential charge. And so that's what happened. I'm going to rewind this because it's actually nice to see. You can see there are two black holes, and then at some point they become one. And in merging, gravitational waves are generated. A lot of energy is radiated out in the form of gravitational waves. And in their last moment, when these two become one, the system shakes itself like a wet dog and gets rid of all the information in form of gravitational waves. If you pick up these gravitational waves by means of gravitational wave detection, you can learn something about the two original black holes and the new black hole. And the size of the interaction that we're going to detect here on Earth is going to be of the order 10 to the minus 21. The only reason I put this number here is because it's small. So gravitational waves were predicted or calculated as a solution of the field equations that were written down in general relativity. In 1915/16, the solution was found, and Einstein said, yeah, that's probably true, there will be gravitational waves, but they're probably going to be too small that we can ever measure them. And he would be so happy, I'm sure, to see that we have detected gravitational waves now. It only took us 100 years. Okay? So when I say small, you have to understand, I'm talking a little bit much about this first slide. I will go much faster later, don't be worried. When I say the effect that we can measure on Earth is small, please don't be mistaken. What we just saw in this visualization is an event where the energy equivalent to the mass of 3 suns, 3 solar masses, that energy is radiated out during that short merger, which takes tens of milliseconds. 3 solar masses are radiated out in the form of gravitational waves. That's a lot of energy. So why the hell is the signal that we can detect so small? The reason is space-time, that is what we're seeing, ripples in space-time, those are gravitational waves. Space-time is incredibly stiff. So stuff happens, but the energy does not succeed in making more than tiny little ripples in space-time. And what arrives at our end, after these waves traveling for literally millions, hundreds of millions, a billion years, what arrives here, when we can measure it, is just very weak. Okay? So this is just setting the stage, and I'm so excited that I'm allowed to be part of the gravitational wave community. Another type of signal that we have seen nowadays with gravitational wave detectors is the merger of 2 neutron stars. These star corpses are indicated over here as these white balls, and the white lines that are coming out are gravitational waves, are supposed to be gravitational waves. And then in this one merger in 2017, in August 2017 that was detected, we actually saw an electromagnetic follow-up to the gravitational wave detection. So we saw gravitational waves first, or we heard gravitational waves first, and then right after that we saw huge amounts of electromagnetic radiation, gamma ray burst, and then all the way from ultraviolet to infrared light, and then X-rays. Over the course of weeks, electromagnetic radiation from this same event was observed. And that's what we like to call the birth of the new type of multi-messenger astronomy. Because now we've seen that gamma ray bursts, for instance, oftentimes come from two neutron stars merging. We also now know that much of our heavy elements is bred in this merger of neutron stars. We know where our heavy elements come from, which people find fancy, so gold, platinum, etc. So that's the other type of event that we've seen. We've seen mergers of binary black holes, mergers of binary neutron star systems. We've also seen, and I only have a very tacky image of that. This is really an artist depiction of what this might look like. It will certainly not look like this. Is a black hole, is a black hole swallowing a neutron star. And I don't have a better picture for this. There's some animations, but they don't show you very much. What I'm trying to show over here in this little image is that in these two events that we measured in 2020, the neutron stars, there were two that were measured shortly after each other, the neutron stars were basically gulped down in whole. So it's not like the black hole tore the neutron star apart, it actually went and swallowed it in one piece. Which is kind of weird. Does that always happen? I don't know. Ask the theorists. So we've seen different types of events. We've seen 90 events to date, which have been confirmed with 5 sigma, and we have 90 events published, and they are all published in the Gravitational Wave Transient Catalog 3. And this image that you see over here is a map of the stellar graveyard. It's what we like to call it, because, let's face it, black holes and neutron stars are star corpses. They're dead stars. Right? And so what we see over here is, sorry, this is making really weird noises. Stop doing that. Okay, good. Okay. What you see over here is the blue dots are supposed to be visualizations of black holes, and orange dots are neutron stars, and when they're half orange, half blue, it's like we don't know what they are. And you can see over here that, for an example, this clicker works differently. Example over here, one black hole and one black hole make another black hole, and the masses are encoded on the y-axis. And this is just a time axis over here. We've seen 90 events. I'm just telling you that we are entering the realm of routine detection of gravitational waves, which is great, because we never wanted to just prove Einstein right. We always knew it was going to be correct what he postulated. What we want to do is do astronomy with gravitational waves. We want to learn about the universe. And what have we learned so far? Well, we've learned quite a bit. We haven't just proven Einstein right again. We have also seen the birth of multi-messenger astronomy with gravitational waves. This gave us the option of constraining the equation state of neutron stars. So neutron stars are like nuclear laboratories in space. We cannot make any this big on Earth. We don't have the money, we also don't have the conditions, right? We are able to localize the gravitational wave sources quite well because we have more than one detector, which I'll show you in a minute. We have, again, tested general relativity, check, still works. It was also an alternative measurement of the Hubble constant. Do you remember that this morning our speaker talked about standard candles, right? He said standard candles. Oops. Does it works better? Yeah, that sounds much better. Thank you. So we now also have standard sirens, because gravitational waves are kind of like the audio equivalent of looking at the universe. We're now listening to the universe. So we now have standard sirens, so we can measure the Hubble constant with a different measurement technique. And we've also shown that there exist black holes in a mass regime that we were not expecting black holes to exist, in the so-called mass gap. So we have intermediate mass black holes. If that's not enough, we're not going to stop here. We're going to build gravitational wave detectors of the third generation, the next generation, with which we will be able to get even more information. And I think I have a couple of slides at the end of my talk to bring you up to speed here. So how do we measure gravitational waves? We do that with so-called Michelson interferometers, and we do it with a network of interferometers. The network is international. We have to work together. We like each other, but we also have to work together. And the reason is, is this better, really? Because it's kind of echoey now. Thank you. Sorry, I'm not an audio expert. Just imagine if you sit in your little lab in your cellar and you measure something. And when you measure something, you can claim that you've measured anything really cool. If nobody can verify that, you can claim whatever, but nobody will believe you. Or they will say, please repeat the experiment because we want to trust that measurement. And I will not go into the anecdote about poor Bill Weber measuring gravitational waves with his bar detector, but never probably having ever measured gravitational waves. For those of you who know the anecdote, it's a sad story. We work together as a network of gravitational wave detectors worldwide, interferometers, and you need at least 2 detectors for so-called coincidence, right? This applies for any measurement. If you want to measure something coming from space, you need 2 detectors on the ground somewhere or in space to tell you in a time-correlated manner, yes, we also saw that, right? Makes sense. Still awake? Good. A third detector will give you better triangulation of the signal across the sky. A fourth detector will give you the option of getting polarization information out from the more detectors you have, just like your GPS signal. If you have more satellites that you can see with your little handheld device, the better the localization will be, right? So we work together in a gravitational wave detector network. The yellow detectors are the ones that are already operational, which is the Advanced LIGO detector in Hanford, Washington, Advanced LIGO detector in Livingston, Louisiana. Both of these are 4-kilometer-long L-shaped Michelson interferometers. There's Virgo, or Advanced Virgo, the French-Italian collaboration, 3-kilometer-long arms in Pisa in Italy. There's the German-British collaboration called GEO 600, which is much shorter and therefore more of a technology demonstrator than an actual, it's a detector, but we are too short to measure, have been so far. And then there's Kagra, the Japanese detector, which is sort of a 2.5th generation detector because it has such advanced technology, cryogenic optics and underground installation, that it is not as sensitive as the others are, but it's using much more advanced technology and will overtake us all. Trust me. And there's one going to be built in, hopefully, in India called LIGO India, which will also be a 4-kilometer detector. What do they look like? Well, they look like this. Actually, no, sorry, that was the electromagnetic follow-up. There you go. They look like this. These are all aerial views, and you can see they are L-shaped, long buildings. And the reason that they all look very similar, L-shaped, long buildings on the ground, underground in this case, is that they are Michelson interferometers. And I'm sure you all know how a Michelson works, right? Show of hands, who knows how a Michelson works? Who would like to have it explained just to recap a little bit? Okay, I'm seeing very timid hands. I'm going to do it really quickly, okay? Light source, preferably a really wonderful laser. I'm just drawn a stupid little light bulb over here. Light source emits a wave, an electromagnetic wave particle dualism. We're going to look at the wave bit. We split up the light on this beam splitter, which is a half transparent, half reflective mirror. The light goes into one arm and into the other arm. If the arms are of equal length, the combination at the output port of this interferometer is going to be so-called constructive interference, right? Wave mountain and wave trough hit each other, are added together. You get the resulting wave over here in blue, described by this blue wave, and that's the field, and then you square it, and then you get lots of intensity. If I now look at this mirror, please, if I now shift one of these mirrors by a little fraction, for instance, n times quarter of a wavelength, then I will have a longer arm and a shorter arm, and the addition of the two waves going in and out will lead potentially to destructive interference. Wave on trough, trough on wave, and you see over here the blue line, no intensity, so no power. And that's called destructive interference. So if the arms move of my Michelson interferometer, if my mirrors move differentially, which is what a gravitational wave does, or if what is the actual thing that's happening, space-time in between the mirrors is stretching and compressing, because it's actually not the mirrors that are moving. The mirrors are free-falling in space. They just hang there and are quiet. But space-time is stretched and compressed periodically by the effect of the gravitational wave. And that is something that can ideally be read out with a Michelson interferometer. Does that function principle make sense? Good, I can see more nodding than blank faces, so I'm going to assume that that has reached you. And this is important because the principle itself is really that simple. And that's great because simple principles are good principles, in my opinion. I'm a simple creature. Unfortunately, it has to be a little bit more complicated because the effect is so small. So we have to use lots and lots and lots of tricks to make a microscopic interferometer as sensitive as it has to be to detect gravitational waves. But at the heart, it is still just a light source. Look over here, laser system. A beam splitter, a half-transparent, half-reflective mirror, end mirrors that are highly reflecting, and an electronic readout, a photodetector. It's still the same stuff with some fancy additions, okay? We have many fancy additions. I would love to tell you about all of them because I like them all and I think they're fascinating, and everything is something that specialists are working on. We don't have enough time for that. So I will just mention that we have the most ultra-stable, beautiful laser sources you can imagine, 200 watts of output power at 1064 nanometers, near infrared, all solid-state laser systems, laser diode pumped, neodymium mag lasers as amplifiers. We're using amplifier stages to get up to 200 watts in the beautiful TM00 Gaussian fundamental mode, spatially, frequency-wise, and intensity-wise stabilized to perfection. Well, perfection as far as technology will let you, okay? These are the best laser systems you could imagine, and we use them, and then we reuse the light by implementing what is called recycling techniques. Very sustainable, huh? We use the light, and then we reuse the light. I will not talk about that, but if you have questions, ask me afterwards. We then also suspend all of our mirrors, all of our so-called test masses in the interferometer, as pendula. And the reason is that you want to decouple your optics, which would usually be standing on an optical table. You want to decouple them from the seismic. What does that mean? Who cares about seismic, right? We're not geologists. Maybe there are any geologists in the room? No. Okay. We're not geologists, so we're usually not concerned with seismic. However, if your mirrors are standing on the ground and the ground is shaking, or you're walking past and you're making the ground shake, your mirrors will shake. If your mirrors shake, it looks like a gravitational wave, but it was just you klutzing around the lab. So what do? You have to decouple from seismic. So you suspend all your mirrors as pendula, and the mechanical transfer function of a harmonic oscillator, which looks like this, will decouple those mirrors from the seismic. So we actually suspend our mirrors as multiple pendulum stages, triple or quadruple pendulum stages. Advanced Virgo has 7 pendulum stages, one pendulum hanging from the other. Sounds weird, right? Trust me, it's true. Again, I could tell you all about that, and I have some backup slides if you're interested. Again, not enough time for that today, but what I want to talk about is squeezing. And now squeezing is a lab slang term. It's really a specific form of non-classical light. Non-classical light is, if you want to have a very simple definition, and I don't think everyone agrees with me, but I like to think of laser light, which is a coherent state. At least I, as an experimental physicist, consider well-behaved, technically beautifully stabilized laser light to be a coherent or a Glauber state. Some people argue that, no, it's not really. For me, as an experimental physicist, good enough for government work. And if you get that beautifully stabilized laser light, and you stabilize away all of the technical noise, you still keep your quantum noise. Quantum noise remains. And trust me, in this device, quantum noise becomes limiting. Isn't that weird? We have something to measure, to test gravitational theory, and quantum effects limit us. So I would like to show you an abstract of someone I admire. He's a colleague called Carlton Caves. I admire many of my colleagues because I have very many clever colleagues. This guy wrote a paper in the 80s. He wrote many papers in the 80s. And he wrote the, I'm going to say, most courageous abstract I've ever read. He says he's going to solve a controversy about whether quantum radiation pressure fluctuations are important in gravitational wave detectors. And this letter solves the controversy. Yes, they do. So, and he's right. He was just proven right a couple of years ago, experimentally proven. So what does that even mean? Huh? So this is what is called a noise budget or a design sensitivity for a gravitational wave detector. It's a calculated budget. You can see there are no bumps and anything in it, so it's not measured, it's just calculated. And over here you see different colored graphs. And all of these graphs represent different noise sources in the interferometer. And I'm going to say something that is fundamental here. If you want to measure something, your measurement device has to have less noise in terms of amplitude than the signal that you want to detect. That makes sense, right? Signal-to-noise ratio better than 1. That's, by the way, a truism. It's a truth of life. If you're listening to someone during a party, you're trying to follow a conversation, and everyone else is making noise, you know what signal-to-noise ratio less than 1 means. Correct? Good. Well, not good, but you now know if I can't increase the power of the signal because I have to take what the universe gives me, the only thing I can do is make my noise smaller. And that's my life. That's my life. Make noise smaller. So over here, you see all of these uncorrelated noise sources that come from different sources in the interferometer. Each and every single subsystem contributes noise, and we have to make sure that we make every single noise source as small as possible. The worst noise source is going to be the ones that are the highest lying ones, because uncorrelated noise adds like the root of the sum of the square of each individual noise source. So the highest lying ones over here are the red one and the pink one. I always make this joke. I did not choose the colors. My colleague Rana Adhikari from Caltech chose these colors. The highest lying source is quantum noise. I work on quantum noise. I have pink hair. I'm sure Rana did not know this in 2014 when he wrote this paper. I don't think I had pink hair in 2014. Anyhow, the highest lying noise source is quantum noise. It's this purple curve that pauses 1 on f squared, and then this purple curve part which is flat, and then it bends up like this. And the other one, the red one, is coating Brownian noise. It's a thermal noise source. Not enough time to talk about thermal noise, but ask me later if you are interested. So what is quantum noise in an interferometer? What is quantum noise in this context? I'll try to explain it briefly and simply. It's a little involved, but I'm taking you by the hand and leading you through this, okay? Because we have the wave-particle dualism, and we're physicists, I'm not really allowed to draw lasers like this, right? I'm not allowed to draw little balls of light in the beam, but I'm still going to do it today. Just to make you understand, laser light is grainy. This is a very bad visualization of the Poissonian photon statistics of your light. Coherent state, Poissonian photon statistics, it's a counting process, and your light will arrive at a photodetector in a grainy way. So there will be sometimes more, sometimes less photons. There will be a mean photon number n bar, and there is a distribution that tells you sometimes you measure more than n bar, sometimes you measure less than n bar. Yes? Good. Everyone's still awake. Perfect. So that's called shot noise. And if I divide by the total power, it's called relative shot noise. And that manifests in a gravitational wave detector in this way. The important thing to remember here is it scales with 1 on root of the laser power. I turn up the power, my relative shot noise goes down. Okay? Good. Flip side of the coin. Same Poissonian photon statistics. I just copy and pasted that image. It really is the same laser. If it hits my suspended mirrors, there is radiation pressure. So I'm not interested in the static radiation pressure. I do not care that the laser light has power 200 watts. We're not using 200 watts. And it blows away the mirror statically. I don't care about that. I'm a quantum physicist. I care about fluctuations. So the fact that my photon number varies, there are so-called amplitude quadrature fluctuations on that light, causes my mirror to be blown away more or less in a time-varying way, in a statistical way. Now the mirror is suspended and it's hanging in the gravitational field of the Earth. So when it gets blown away more, in the next instance of time when there's less light impinging on me, the mirror will fall back into its position of equilibrium due to the restoring force of gravitation, right? That's what pendula do, they fall back. That means the light pushes the mirror and the mirror pushes back on the light. And that is called back action. Does everyone in the room understand this concept? Great, because if you understand back action, you have understood quite a bit more than many other people working in the field. Because back action is a way of coupling amplitude quadrature fluctuations. The mirror is now pushing on the phase of the light, which goes into phase quadrature fluctuations. And that is so cool because it's basically mechanical squeezing. It's ponderomotive or opto-mechanical squeezing. You're coupling the two formerly uncorrelated quadratures of the light. Isn't that great? It's also terrifying because it means that now we have to deal with 2 different noises. Ugh. But it's okay, we can do this. So you understand this? Good. The last bit I show you over here is, unfortunately, my quantum radiation pressure noise scales conversely to my relative shot noise. So if I turn the power up, over here, scales with root of p, if I scale the power up, my quantum radiation pressure noise is also going to increase. But that makes sense, right? More power, more fluctuations, more mirror interaction. Yeah? Good. So there is no easy way of doing this, right? I can either, it's back action noise, there's detection noise. I can either turn the power down, then my radiation, no, what did I do? Okay, I can either turn the power down, then my relative shot noise goes up and my quantum radiation pressure noise goes down, or I can turn the power up, and then my relative shot noise goes down and my quantum radiation pressure noise goes up. What you gain on the swings, you lose on the roundabouts. There is an optimum, but that optimum is power dependent. It's the intersection point between these graphs, here, here, or here. And if I keep this running, you can see this curve moves on another curve, this intersection point moves on the so-called standard quantum limit of interferometry. Now, I have taken you by the hand and led you through 2 semesters worth of quantum optics stuff. But, you know, that's a good deal for a Thursday afternoon, I guess. So it's really not that easy, at least not by a simple means of turning the power up and down, to go below that SQL. So that's kind of a very hard to reach regime in that orange shaded area. But we can do it. We can do it. I need to up the ante a little bit, so I still have time for you to ask some questions. So I'm going to rush a little bit more. But it was important for me for you to understand the fundamentals of this and the basics, because I think most of you, I'm assuming, are students or PhD students. Is that correct? Good. So I guess not all of you are in the field of quantum optics. So simple stuff. This part you should all know. Time series of your electromagnetic wave is this, and the fuzziness is very, very strongly exaggerated, the quantum noise. It's not that big, but we're just going to draw it that way. And if you want to know more about this, by the way, this is an amazing review that you can read on the quantum noise characteristics in interferometry. It's really good. Written by a personal friend, Stefan Danilischi. So you can also represent this in a phasor picture. Over here is your coherent excitation, this red arrow, and that tip of that arrow can be anywhere in the blue dotted area. That's your uncertainty. Right? And so I can write it like this. This is a coherent state. Now I've swapped the colors, red and blue. And I can define quadrature operators, which are x1 and x2, amplitude and phase quadrature operator, which are defined by the annihilation and creation operator. This is all quantum optics standard basic stuff. And then I can define uncertainties, because Heisenberg just says, well, you know, the product of those 2 uncertainties cannot be smaller than a certain value. I'm going to say 1 as a good theorist, which I'm not. It doesn't say that it has to be exactly 1. It just says more than 1 or 1. It doesn't say that the 2 uncertainties have to be of the same size. And that's already the secret behind squeezing. You just pick which one of the quadratures is more interesting to you and say, I want the uncertainty to be smaller in that. I want to squeeze the uncertainty to a smaller value in that quadrature, in that observable. And I don't care about the orthogonal quadrature. I don't care about that. And that's squeezing. You can see over here, here's your coherent state, here's your squeeze state. Because Heisenberg only says larger than or equal to. And there you have it, that's squeezing. How do you produce squeezing? That would be a topic for another lecture of about at least 45 minutes. It's a fairly complicated breadboard. This is, by the way, the actual breadboard that was used in the gravitational wave detector GO600. Has about 200 optical components, 3 lasers for different locking schemes. Here's a simplified schematic, and here's the actual breadboard. And here's an image of what it looks like in a gravitational wave detector, at least in GO600. These are average-sized German men in bunny suits, so you can see how big this thing is. It's about 1.3 by 1 meter. And it weighs about 100 kilograms, I think, approximately. So this over here is the actual squeezing bench. Okay? Pretty elaborate system, I guess. Now, what does it do? What does a gravitational wave detector profit from using squeezed light? Without going into too much detail, I can tell you that, remember we said signal-to-noise ratio is important. I need my measurement device, my gravitational wave detector, to be as quiet as possible such that I can hear tiny little gravitational wave signals pop up over my noise. So this over here in blue is the gravitational wave detector GO600, very many spikes in there. Ignore the spikes, look at the envelope. This is the gravitational wave detector without squeezing. This, in red, is the gravitational wave detector with fixed quadrature or phase quadrature squeezing. So lower in noise is better, right? Signal-to-noise ratio, well, signal same size, noise down, better. That's exactly what we do. And the amount of squeezing we have in the interferometer is 6 dB, which sounds, well, to me, hugely impressive. To you, maybe not so impressive. What that means is that we have been able to increase the sensitivity by, well, by a small factor. But the good thing is that we can now actually improve on that, because we can actually produce a lot more squeezing than just 6 dB. We can actually generate things like 12 dB of squeezing or even 15 dB of squeezing. The problem is that because squeeze states are quantum mechanically sensitive states, the actual magic lives in the entanglement between the photons that live in the sidebands. If you lose one of these photons, the entanglement is gone, which means the correlation is gone, which means the degree of squeezing degrades. And that's why squeeze states are such sensitive little creatures. You have to be very careful with them, and any kind of loss, optical loss of light, will hurt your squeezing, will harm your squeezing. And that's why getting 12 dB or 10 dB into an interferometer and getting out 6 dB in the interferometer is a heroic effort. So I want to show you why Carlton Caves was right in 1980. I still really like this result. It's now from 2020. I think it was measured in 19 and then it was published in 20. This is an actual measurement of the sensitivity curve of the advanced Virgo detector. It doesn't look like the calculated thing because we're zooming in. What we're seeing over here is normalized to shot noise, is the behavior, the noise behavior of the gravitational wave detector if you send in the correct type of squeezing, and if you send in the incorrect type of squeezing. You can squeeze one quadrature at the cost of the other, or you can squeeze the other quadrature at the cost of the one, right? We're going to squeeze the right one, and then we get an increase in sensitivity here, or we can squeeze the wrong one, and then we get a decrease in sensitivity here. Do we? Do we really? Do we get the effect that I was predicting? If you improve relative shot noise behavior, do you get an increase in quantum radiation pressure noise? And if you zoom in really closely here at the low frequency end where quantum radiation pressure noise dominates, you can actually see over here, actually I'm not sure if you can see, that indeed the red curve goes down, which is good at high frequencies, but at low frequencies the red curve goes up. We see the effect of quantum radiation pressure noise increase due to the fact that we have shifted that uncertainty into the uninteresting quadrature. We see that at low frequencies. And what that means, you have to savor this moment, okay? What we're taking is vacuum noise. Vacuum is not nothing, right? A coherent state has a coherent excitation, and that ball on top, this uncertainty, that's vacuum noise. And this vacuum noise is, well, mostly you measure nothing, but there are still photons inside. If I now squeeze that, I am modifying the photon statistics by actively shifting around individual pairs of photons in a photon stream that is on the order of 10 to the 16, 10 to the 18 photons per second. So many, many photons in your coherent light, very few photons contained in your vacuum noise. And this gentle modification of your vacuum state causes the mirrors in advanced Virgo, which weigh 42 kilograms, to shake in excess, because that's quantum radiation pressure noise. Does that not boggle your mind? You're modifying vacuum state, and your mirrors start to shake more because of a whiff of nothing, just a lick of light, just a tiny little bit. I find that quite fascinating. So we now have seen macroscopic quantum optomechanics. Our mirrors move more, our macro 42 kilogram mirrors move more because of the interaction of light with the mirrors. And that's okay. It just means that if we want to go a step further, it's not enough to squeeze one quadrature and anti-squeeze the other. We have to do something else. And that is called frequency-dependent squeezing, and is a story for another time. In the remaining, 5 and a bit minutes, I would like to tell you much, much more about what else you can do with squeezed light, because that's what I work on. I work not on this baseband squeezing, which is used for gravitational wave detection. I work on squeezing combs. And these squeezing combs are a specific type of light source. They use parametric down conversion like the gravitational wave detection squeezers do. And they look in my lab like this. There's a little crystal here in this little focus, which you can't see. It's periodically poled potassium titanal phosphate. It could also be lithium niobate. For different wavelengths, it could be BBO. It could be all sorts of different nonlinear material. It's crystal, which gives me parametric down conversion. And I build, or my group builds, an optical resonator around it to have cavity-enhanced squeezing. We never say that because we always use cavity-enhanced squeezing. Because the Chi2 medium that we're using here has it has a strong interaction in comparison to other media. It's still pretty weak. Chi2 is quite weak. We build a cavity around it, and that cavity could have 4 mirrors or 6 mirrors, or it could even have 12 mirrors like this one. Wait, 1, 2, 3, 4, 5, 6, 12 mirrors. And with that, I can build pretty long optical resonators. I make that length of my optical resonator usually 1.5 meters long, which corresponds to a free spectral range of our cavity of 200 megahertz. Every 200 megahertz, I get an enhancement of my light field. Any one of you who's ever done any cavity stuff in the lab knows that's how cavities work, yes? Who's done cavity stuff in the lab? No one. Oh my goodness, that's shocking. You should do cavity stuff, it's really fun. Simple, Fabry-Perot interferometer, 2 mirrors. Only half wavelength multiples fit inside, right? Otherwise you don't have resonance. If I shift this by a half a wavelength, or actually a quarter wavelength, so I have there and back is half a wavelength, then I get the next free spectral range, and another quarter wavelength, new free spectral range. So if I have a piezo electric transducer on my mirror and I zoom the mirror, I sweep it through, then I get nothing resonance, nothing resonance, nothing resonance. You're familiar with that, right? Airy peaks. We all know it, at least from our studies. That's exactly what we're doing here, only that this time there's an active medium inside and we get parametric down conversion and enhancement every free spectral range. Now you know what we're looking for, I hope. And these are just some more dates about my laser. About my squeezer, I'm just going to ignore that. Squeezing means that you get a reduction of your noise below the shot noise of your laser. And you see over here, we have in our lab 200 megahertz here. We have a reduction of our noise which goes below 10 dB. So a factor of 10 decrease in noise relative to the shot noise over here. The cool thing in our lab, however, is that we don't just have that at 200 megahertz, we have it at 200, 400, 600, 800, all the way up to the end of our detection capabilities. And that looks like this. I'm going to scan this, hopefully it'll work. Let's see. Does it work? There you go. The axis on the bottom is running. We're now at 3.6 gigahertz. And you can see that the graphs basically stayed the same, because we have squeezing every single free spectral range, which then looks like this if you look at it all simultaneously. So here's your frequency axis at the bottom from DC to 3.5 gigahertz, and you get a reduction every single free spectral range. Why is that cool? Because you can use it for many things. You can, for instance, do spectroscopy with this. And the reason why I'm so excited about doing different things with squeezed light is because whenever we were asked many years ago, what can you do with squeezed light? The answer was always, gravitational waves. And now we can say, well, yes, obviously gravitational waves, and it's awesome, and we would not be able to detect as well as we can if we didn't have squeezed light. And my colleagues that are doing this are magnificent. They do great work. But you can use it for other things too. And isn't it great if you can take your car on a trip to go camping, but you can also use it to help someone move their furniture, right? So cars are also multi-use. So is squeezing. That was a really bad analogy, I'm sorry. Couldn't think of anything else right now. So squeezing is also useful for spectroscopy, and we've done it. If you have a spectroscopic signal, and it's kind of small, and it's at low frequencies, that can be a problem, because at low frequencies, you very often have a lot of technical noise. Any one of you who's done any work in the lab knows at low frequencies, noise is always a pain. So what do? Well, clever spectroscopist people know that it's always a good idea to shift your frequencies to higher frequencies by modulation techniques and then hopefully escape the technical noise at low frequencies. But what happens at high frequencies is that oftentimes shot noise becomes dominating. You know, you escape one, you find another. What do you do about shot noise? Well, now we have squeezing, and we can lower the effect of shot noise by using squeezing. And then suddenly your signal pops up above the noise level. And that's exactly what we did. Increase the signal to noise ratio. You can see a theme here, right? increase the signal-to-noise ratio, and experimentally we do it like this. We take our source, we modulate it, put it into our squeezer, so phase modulation, put it into our optical parametric oscillator, our down converter, have a squeezed ellipse, put this onto our measurement spectroscopic cavity, move the cavity mirror around as a spectroscopic signal, the one that we weren't able to resolve beforehand, and then have modulation sidebands on the modulation sidebands. And if you look at the signal, we do a homodyne detection, which is a phase-sensitive detection, and then you get you can detect the low-frequency phase modulation signals in the amplitude quadrature of your now detected signal. And it looks like this. Here's your shot noise in red, and in blue, you can see the lowered shot noise level, the squeezed noise level. This is my carrier, the initial modulation from the EOM, and these are my signal sidebands at, in this case, 20 kilohertz left and right of that carrier, which would not be visible above shot noise, but they're visible on the lowered noise source, on the lowered noise floor. And we cannot just do this with 20 kilohertz, because where's the challenge in that? We can also do it with 100 hertz, and that's kind of nice. So spectroscopy can profit from squeezed light. Can we do something else? Yes, obviously. We can use the fact that we have squeezing at every free spectral range of our optical parametric oscillator. That means that this process uses parametric down conversion. I sort of mentioned that in a half sentence. What that means is you put pump light in, and I'm going to wildly switch to the photon picture here. I take one photon of the pump source, and I chop it in two, and I make two entangled photons at the fundamental. So second harmonic generated photon, put it into my crystal, make two photons at the fundamental out of it, and these two have quantum correlations between them. But whether these two photons turn up at baseband, or at the plus-minus first sideband, or at the plus-minus second sideband, energy conservation, or at the plus-minus nth sideband, does not matter. They always turn up pairwise, and the entanglement lives between them, which is why the loss was so bad. If I lose one, entanglement gone. So I have this beautiful squeezing comb with the entanglement living between the nth sidebands, plus-minus n sideband. If I then take this squeezing comb and split it up by means of an unbalanced Mach-10 interferometer, I can get two outputs where all the even order sidebands are common mode, and we ignore them. We don't care about common mode. Differentially, all the sidebands at -5, -1, +3, +7, and please expand to the other sides, turn up at output A, and at output B I get the other ones, -7, -3, +1, +5. If I now put these where the entanglement lives between these sidebands, I'm going to flip the bottom axis. So now you see -5 and +5 are related. If I now put a homodyne detector symmetrically between them, I still do not have entanglement between -1 and +3, but I have entanglement between -1 and +1, and I have entanglement between +3 and -3. If I put these individually onto a homodyne detector with a frequency-shifted local oscillator, I can then put these two into relation by doing a difference and addition over here, and I can generate entanglement between pairwise non-entangled sidebands. And the cool thing about this is that all the quantum information people get really excited about this, because this is an EPR comb. You can build cluster states out of them. You can do frequency multiplexing in quantum communication, and you can do quantum information with them, entanglement swapping and entanglement teleportation. So this is the quantum information application potentially for squeezing combs, which we're pursuing. And if we go back to gravitational wave detection, I'm going to skim over this, otherwise you don't have time to ask any questions. So I told you that doing one type of squeezing one and not caring about the other, is going to stop being very effective, which is why these days we are going to start doing, so next month, the new observation run of our gravitational wave detectors is starting in May, 28th of May or so, 26th. And we're going to be using something which is called frequency-dependent squeezing. So we get the right squeezing at each frequency. We get the phase quadrature squeezing at high frequencies where relative shot noise is limiting. We get amplitude quadrature squeezing at low frequencies where radiation pressure noise is limiting. And in between, we get so-called quadrature squeezing. The squeezing ellipse moves over frequency. And the reason for that is that we can then take a big chunk, a big bite out of this sub-SQL area, which we were formerly not able to access. And this was proposed many years ago, but trust me, it's experimentally incredibly challenging to build. Tabletop experiments, difficult enough. large-scale detectors with 100-meter-long cavities, a nightmare. But my clever colleagues have done it, so I'm in awe. Is there a possible alternative? Yes, my group is investigating one. I'm going to actually skip this because otherwise you will not have enough time to get the end of the talk, and I don't want that. I want you to be able to get as much as possible out of this. We're doing a different kind of radiation pressure noise cancellation, which is called coherent quantum noise cancellation, with which we can then destructively interfere away parts of the quantum radiation pressure noise. Now, while we were investigating this, our crystal broke. Why am I telling you this? Because I would like to impart on you something else that you might not learn from other professors. Sometimes life sucks. And that's not good at the time, but don't despair, because sometimes when you are forced to solve a problem that you're not expecting and you have to work around something because something broke or something is not deliverable, or sometimes you come up with really cool new ideas to fix it. So please don't despair immediately when something breaks. Sometimes it leads to something new, which is also good. It doesn't feel like it in that moment, but when you look back, I can tell you sometimes that really happens. Not all the time, but often it really does happen. What did we discover? We didn't have another crystal. So we said, okay, we're going to use a different crystal, but that crystal doesn't work the same way. We're going to use a detuned optical parametric oscillator. We're not going to run our squeezer on resonance. We're going to run it next to resonance and see if that does the same thing that this broken crystal would have done. And it turns out, yes, it produces frequency-dependent squeezing, as it should. So you can see over here this turning squeezing ellipse that I showed you earlier in the little schematic. Here's a turning squeezing ellipse, and I'll actually show you a little GIF. You can see over here, it's not, okay, you can see, look, it's squeezed in that direction, and then it turns back into a vacuum ball, and then it turns into a squeezing ellipse, and then it turns back into a vacuum ball. And this is frequency-dependent squeezing from a detuned single-mode squeezer. We're really happy with this result because that can actually lead to something completely new. So from bad things, sometimes good thing happens. And also something which might be a little unusual. This is a German comic, so there's an English inaccuracy in here. Is this all he can do? Right? This is anyone familiar with Grimm's Märchen, with Grimm's fairy tales? There is this Tischlein deck dich. There's this little parable of the three sons that leave the house, and then they're supposed to learn how to be a tradesman, and they come back with goods, and one of them comes back with a donkey, and when you lift the donkey's tail, gold comes out, right? And now the joke here is, if you have a donkey that is pooping gold, that's a good thing, right? You don't need it to be more than a one-trick pony. It suffices if you can make gold, right? I'm not sure if this is really reaching you, because I think it's hilarious, because the squeezing is not a one-trick pony. You can do so many things with it. You see the irony here, right? So is this all you can do? Yes, the squeezer is a very good resource for many, many different things, and I don't have time to go to the next generation with you, unfortunately, but I will tell you that obviously it does not stop here, right? We're not going to stop at the second generation of gravitational wave detectors. We're going to build a third generation, which is currently under discussion. There's something called Cosmic Explorer in the US, and there's something called the Einstein Telescope in Europe. If you hear about the Einstein Telescope, please always tell your politicians and your teachers, Einstein Telescope, we need it because we want to be a full partner in the worldwide endeavor of measuring gravitational waves. There will also be a space-based gravitational wave detector called LISA, Laser Interferometer Space Antenna, and hopefully at some point we'll have a detector in Australia as well. And this Einstein Telescope, which is a European project, is very close to my heart because I'm involved in the collaboration, and I think it will be a very good test bed to, and a very good, how do you call this, innovation forge to solve a lot of problems that gravitational wave detection currently has. So it's going to be an underground detector, 10 kilometers in side length. The observatory will be triangular, containing 6 interferometers, 2 per V, 1 low frequency, 1 high frequency, and then 3 of these detectors, 1, 2, and 3, in blue, green, and red, which gives you in total 6 interferometers. And if you look at the sensitivity, we're back to signal-to-noise ratio, of the advanced LIGO design over here in blue, you can see that the design for the third generation detector Einstein telescope is going to be more than a factor of 10 better. And that sounds like not very much, right? A factor of 10 doesn't sound terribly impressive. But think about this. If I am 10 times more sensitive, I can see 10 times further in this direction, in that direction, and in that direction, which means I have a 1,000-fold larger volume of the universe I can observe, which will mean for the Einstein telescope, we will be able to virtually hear every single binary black hole merger back to Big Bang. Not that there were any black holes there at the time, although, listening from this morning's talk, primordial black holes are back on the menu. People are actually investigating this again. So, having said that, we will be able to listen not quite back to Big Bang, but quite a lot further into the past. And if we can do that, we have an observation range, which is given here in redshift, by the Einstein telescope given in green for large masses. So our low frequency sensitivity is very good, which means we can then measure very large masses, mass mergers with the Einstein telescope. And with that, we should hopefully be able to not just hear binary black hole mergers, binary neutron star mergers, neutron stars being eaten alive by, or dead, by black holes, but maybe also supernovae, which could, well, this is also an artist's depiction, look like this, but it would actually sound like this. But I would really rather have the original sound bite from the gravitational wave detector and detect gravitational waves from supernovae, or detect gravitational waves from asymmetric spinning neutron stars, so-called continuous wave signals, because if a neutron star was not perfectly round and spherical, if it had a little bump, a little pimple, we should be able to measure that. We're not able to measure it yet. With the Einstein telescope, we will. The vote is still out whether neutron stars are perfectly round or not. We will also hopefully measure sources that we were not even expecting. But that remains to be seen. And with that, I think I'm at the end. This is a picture of parts of my group, and I hope I have a few more minutes for questions, if that's okay with you. Thank you.
Thank you so much.
You're welcome.
It was a really impressive presentation. It was unexpected for me that here in the country of laser, in this audience, no one has worked with the resonator. It seems that we have gathered today only theoreticians. Okay, so dear audience, participants, do we have any questions? Yeah, so Vytautas Žalandauskas.
What she said. Thank you for the presentation. I was wondering about how would you actually realize the scheme of the Einstein telescope? Would you put these three telescopes in Lagrange points? And which one of them would have the squeezer, optical?
Okay. Very good questions. I did not make this clear enough. The Einstein telescope will be a ground-based detector, so yes, it will not be in space. Should we go outer space now? Yeah, I said LISA will be in space, yes, and yes, that will actually be, I do have, maybe, let me see. I probably do have slides over here. Let me just check. Of LISA, maybe. I can tell you in words, though, using my hands. LISA is a laser interferometer space antenna. And I don't have any slides on that, I'm sorry. Laser interferometer space antenna will be 3 satellites in space in a triangular geometry, 2.5 million kilometers apart, which will follow the Earth on a heliocentric orbit, turning around each other once per year, such that this orbit of the individual, just a bit like these triple rings that you can know, it looks a bit like those triple rings, right? So that it reproduces its orbit once per year, and that will be in space. The Einstein telescope will be on the ground. It will actually be underground at about 200 to 300 meters depth, in stone, if possible, nice and homogeneous, geologically quiet, boring stone. And thereby we can eliminate the effect of what is called, well, not eliminate, but mitigate the effect of what is called Newtonian noise, which is the existence of mass on Earth influences the measurement because the masses of the mirrors are also attracted by mass. And if those masses, it sounds terrible, right? But if the masses of the environment move around, like if water flows through the stone, like if there are what do you call that? Klüfte. If there are like holes or like tunnels or splits in the stone and water flows through it, that's a time-varying mass signal. And then the mirrors will actually move, and that looks like a gravitational wave. Isn't that, like, it boggles your mind, right? If there is atmospheric pressure changes in the tunnels in which this will be housed, makes a difference. If clouds go over the countryside, we can actually, it has an effect. That's how sensitive these things are. And so the Einstein telescope will be built underground as opposed to Cosmic Explorer, which will be, they are going to go for longer arms, but not underground. We're going to go for not much longer arms, but underground to go to low frequency sensitivity. And the reason why it's triangular is actually, you could also build it as an L, but then we only have the advantage of being underground. We don't want to be the little brother of the American detector again. Okay? So don't get me wrong, there's a political reasoning over here, but what I'm trying to tell you is that there is a really cool reason to have this V, V, and V. You can always calculate an L out of it, but you also have an automatic null stream. You have a dark measurement, so to speak, because you can always calculate a null stream, right? So there's many reasons why this triangular configuration with the V and the V and the V is very good. And the reason we split into low frequency and high frequency is because the noise sources, as you can see in the budget, are different for low and for high frequency. So you can optimize, if you have two interferometers that are co-located but have different technology, you tackle the problems individually. So that's a very clever idea, in my opinion. And very good question. Thank you.
Okay, we have another question. So, Bonn University, Mindaugas Šarpis.
Thanks. Yeah, really, really nice talk. I think it was really amazing. I had the normal question, and then I came up with a totally crazy question. So I'll ask the crazy question.
You're at the right address.
Are you familiar with cyclic conformal cosmology a bit?
No. What?
No. Okay, so then I will phrase my question accordingly. So you showed, or we know that we can kind of detect black hole mergers. Mm-hmm. Now I think that sensitivity brings us to neutron star mergers and so on. There are these events where black holes evaporate in space, and when they evaporate at the very end of their life, they do a small pop, but the small pop is about 200, 500 Hiroshimas worth of small pop, you know. So it's in cosmology or in space, in astronomy, it's tiny, and for gravitational waves, it's probably nothing. I don't know the magnitudes you work with, but it's nothing compared to a neutron star merger or something. But I know that, so Roger Penrose talked about this. If we started, and if we could detect these small pops of gravitation of black holes, we could probe what happened before the Big Bang, if anything happened before the Big Bang. Okay. So the question is, do you think with, let's say, the space-based, interferometry experiments and so on, are we reaching that precision, or is it 200 years in the future?
So the actual sensitivity, so your question sounds like a Penrose kind of one. Yes, very good. When you said it's going to be a slightly interesting, exotic question, that makes sense. Is it like a cavitation thing? Like it just ceases to exist and gives that like little... Yeah, it's like a cavitation bubble, right? Cool. I need to read up on that. We need to talk. LISA, so the gravitational wave detectors on the ground, like advanced LIGO, have this sensitivity curve that looks like a bucket, right? It looks like this. The LISA sensitivity curve is actually not more sensitive. It's about the same sensitivity. It's just at a different frequency range because the arms are longer, and so we're sensitive to different frequencies. And we're also sensitive to different frequencies because this Newtonian noise that I talked about, this gravity gradient noise, does not occur in space because no mass. Right? So that's why there's pros and cons. You need both. You need space and ground because they have complementary measurement regimes. So it's not so much the sensitivity that bothers me, it's the frequency range. And I do not know, a pop is a transient signal. It sounds to me like that would be something that is not low frequency. But I don't know, so we should talk more. And maybe the good part for everyone else that is not interested in cavitation bubbles of ceasing to exist black holes is the fact that LISA, the Laser Interferometer Space Antenna, which will hopefully be launched in 2035, we hope. It's one of the large ESA missions. It's an L mission of LISA. You just saw that JUICE was launched, right? then comes another one, then come we, right? So for you, maybe important is the fact that the sensitivity is actually not, it's not like here's ground-based and here is Lisa. No. It's here is ground-based at frequencies that are in the audio band, hertz and more, and here is Lisa at millihertz, which is in order of even a little bit less in sensitivity. However, imagine this, 2 black holes merging means that for many years, black holes approached each other and then started dancing around each other at long distances with very, very long time constants. You could have seen that first merger that we detected on the ground with Lisa 10 years ago, because you could have seen that, you know, it's like a courting dance of these 2 black holes that are dancing to death. You could have seen that slow in spiral many years with Lisa, but we don't have Lisa yet, so you have to campaign for Lisa as well, okay? Cool, thanks for the question. And please, really, I want to know about this cavitation stuff.
Okay, any more questions from the audience? Okay, Christopher Bagdonas. I know everyone.
Thank you for the lecture. It was very interesting. You said those telescopes, would it be possible to make a lot of gravitational telescopes and make a picture of the sky and the gravitational sources?
It's not a matter of, it's a very good question, and people have asked me that as well. Like, could you do Hubble Space Telescope pictures or James Webb Space Telescope pictures with gravitational wave detectors? But we're not limited in resolution, so to speak. Yes, more detectors would be great because we get better localization and better verification, but we're already very good in terms of that with the detectors we have. It is, you're not looking at a field, you're not looking at a spatial distribution, you're looking at one event, and if you saw multiple events at the same time because you're so sensitive, you could still extract those from the basically time series. We're taking a time series measurement of our gravitational wave detector stream, the output, the photodetector output at the electronic eye, and we see things that the waveform actually looks like for a binary black hole merger, looks like wave noise, and then suddenly you see something go like this, and then you go, it sort of looks very noisy, and then it goes, it just rings down like that. Oh, sorry, all the sound effects are just my excitement about gravitational waves. So what you see is this dance of death where they're basically very, very periodically and rhythmically spinning around each other, and then the intensity increases because they're getting closer, more radiation is being radiated out, more gravitational radiation. The merger is dirty. You see, it just mushes together, and they actually, if you see simulations of it, there are beautiful false color images of the simulations, hydrodynamically calculated, relativistically hydrodynamically calculated simulations of what happens when 2 black holes just mush up. And then after that, as I said, the new system is a new black hole, and it's basically like nothing happened. And that's when it's rang down like this, and then nothing happens anymore. And then the signal, the time series just keeps just noise. If we saw many of them, you would have to somehow disentangle the individual measurements, but you could still do that. And the good thing about multi-messenger astronomy is when we know what's going on, and with the gravitational wave detectors, we can quickly pinpoint it's coming from there in the sky. You can ask all your friends from the electromagnetic telescopes and say, have a look over there, and then they can look at all, if we do have electromagnetic radiation, they can quickly look over there and say, oh, look, now's the gamma ray burst 2 seconds later, and now is visible light and infrared light, and now comes X-rays. So yes, more detectors is good and important, but it's not like we are looking at a spatially resolved picture where we have to scan or we have to have an array. We don't need that.
Okay.
Very
Any
good
more
question
questions? And okay, once again. Okay, so I will take a lead as chair, and after. So first of all, this abstract which was shown, it was from PRL journal, because today we had like a nice seminar from Nature Communication editor, and he said like 50% of acceptance rate depends on the motivation and the abstract part. And For me, it's questioning if the sentence, yes, they do, can be applied to Nature journal. But for Pirel,
I have a feeling that the time for these kind of abstracts is not there anymore. Like, I don't think...
Like from,
if I was not in an official setting, I would use more harsh words, but I don't have, let's say, the backbone to write an abstract like that. Carlton Caves does. He already had a good reputation at the time.
Yeah, you should before have a reputation. So my question would be about single-mode squeeze states. We have been used for quantum sensing. However, if you want to go farther and expand your research, for example, go to quantum communication, quantum computing science, you need multi-mode spin squeezing states. Yeah? It's the answer. So is it possible to use single-mode squeezing in order to generate multi-mode squeezing?
Yes, it is.
Yes, and for LIGO experiments, single squeezed mode is enough, or should go beyond?
At least for the current iteration, we're using... And so you've actually asked a very subtle question here, because in my opinion, nothing really is single mode squeezing. Okay. In my opinion, because you have two entangled sidebands, just because they look indistinguishable, because I cannot tell apart 1 megahertz difference, does not mean they're indistinguishable. It's just that I cannot distinguish them. So it's a subtle question, but if you go one step complexity back, we use single mode squeezing in ground-based gravitational wave detection. We will, by the way, never use squeezing in LISA, because quantum noise will never be limiting there. It has a completely different operation principle, which I didn't have time to talk about. Again, if you're interested, ask me. But we can produce EPR entangled states by using one single mode squeezer and another single mode squeezer, putting those two on a beam splitter and making two entangled states which individually look like thermal states. If you correlate them, you get your typical EPR entanglement out. You can also use two-mode squeezing, which is frequency or spatially, which is usually the same, or polarization non-degenerate squeezers, and thereby generate two-mode squeezing.
Okay. I had a question how you travel from squeezing from one quadrature to another when we talk about low frequencies and high frequencies, what happens. But you already answered it nicely during your presentation. So we have like time for the last one question. We have one candidate from CERN, but more? No? So two candidates. Okay, so Center for Physical Sciences and Technology and CERN. We will end up with Mindaugas, with crazy questions. Yes. So.
I was just wondering which quadrature squeezing was the more frequently used, the amplitude or the phase one?
Phase quadrature squeezing, because that is the one that, if you remember, the relative shot noise was detection noise, and that is kind of, you know how you call it shot noise because when. You know what they mean by shot noise, right? In German, it's Schrotrauschen, which means Schrot is the stuff that you use, I hate to say it, but you use to shoot animals with, right? You know, it's not one bullet, it's like this grainy stuff that you shoot. I would never shoot an animal. I would never shoot anyone, actually. But it's okay, going too far. And the reason it's called shot noise is because it doesn't make poof, it doesn't make like a ting, it goes like rain falling on an umbrella, right? And that is really the phase spread in a way in your light, which is why you want to reduce the phase quadrature uncertainty in that to reduce the effect of shot noise. And so that's the one that's been used so far, because there we were dominated by quantum noise. At low frequencies, quantum radiation pressure noise we didn't even see. This is the first time now since 2020 that we actually are able to see a little bit of quantum radiation pressure noise, and then we'll have to go to the frequency-dependent squeezing.
Okay, so thank you. Thank you for the question, Vituti, quantum sensing expert. So the last question goes to Mindaugas Šarpis.
Okay, thanks. Yeah, so a funny question. It's kind of on the topic of ground-based laboratories versus, space-based. It might be a lack of my understanding or something, but if I understand correctly, Earth is kind of a ball of mass floating in space. And now if you detect your gravitational waves on Earth, with LIGO and with these, Einstein telescopes and so on, I imagine the mass of the Earth should have some sort of attenuation effect or something on the gravitational wave, because it's not vacuum, there's something there. you don't have that in space, but will there be some effect which needs to be accounted for when you do the ground-based experiments, or it doesn't matter at all? I don't know.
Because masses are embedded in space-time, and I would also be deformed by a gravitational wave. If there are always gravitational waves coming in, they're just really weak, and I would be sort of stretched and compressed all the time, and so is the Earth. It's also breathing, but it doesn't matter. It really doesn't. The thing that is really limiting is the effect of time-varying mass distribution changes. And that's this Newtonian noise that I talked about, and that's a pain. Thanks.
So closing remark that each time you go outside and look at the night sky, think about gravitational waves, LIGO, remember that somewhere in Germany we have a professor who works how to precisely measure all this noise which comes from the space. So, Professor Michèle Heurs, thank you so much.
You're welcome.
Let's loud applauses.
Thanks for all the questions too.